Hello and welcome to another A-level physics video. So today we're doing mechanics, and specifically we're going to look at the constant acceleration equations. So here are the four constant acceleration equations. Technically you can get another one by just rearranging for use in this formula down here, but these are the ones that you should remember. Now, some students kind of wonder, how can you memorize these? Honestly, I wouldn't bother memorizing them. All I would do is I would just go through and make sure you understand all of them and just practice as much as possible. The more you use them, the more you'll be able to remember them. If you do A-level maths, honestly, I'd be surprised if you don't remember these. But let's go through some key points. Now, shockingly, you can only use these when acceleration is constant. Now, you might think that that's a bit obvious, right? You probably clicked off the video by now. But keep in mind that a lot of the times in physics, they will ask you, after you do a calculation, why is it not accurate? Why is there only an estimate? Why should the time be longer or the speed be lower or whatever? It's always because the acceleration is not constant. Okay, and then you have to think of why. Has air resistance been taken into account, for example? These are some things that you can think about. So, what kind of situations can you expect? Well, anything falling, really. Because when anything falls, then gravity is just equal to 9.81. Right, so your acceleration is just 9.81. Now again, sometimes they may include things like, to be honest, with SUVAT equations, you don't have to worry about it. They'll give you the acceleration if it's not 9.81 when you're dropping something. But some other examples are accelerating uniformly. So if they ever say something is accelerating uniformly, that is the exact same as saying it's accelerating constantly. Okay, so if any of that is implied or used, then you can use the SUVAT equations. The other time they may say accelerating uniformly is if you have a velocity time graph or even an acceleration time graph, which is flat, right? So no gradient, or a velocity time graph with a constant gradient. So those are some of the things that you can do to include those. Some other things you can think about is if something's in a vacuum chamber, so that just means all of the air has been sucked out of it, which means if you're moving things around, there's no air resistance, so it's very, very close to having a uniform acceleration. So these are the kind of situations that you would want to use these in, but again, it is fairly obvious, and they'll either say it's dropping if something's falling, and they'll say ignore air resistance, or if something's accelerating uniformly. So let's go on to some questions. So I've gotten exam questions from various different exam boards, but keep in mind with SUVAT especially, it's basically the same in all of the exam boards, right? Because it's SUVAT. It's very common. So you'll find a lot of overlap, but I have got a couple from each exam board. So here it says, a vehicle that skids can leave a mark on the road surface. This skid mark can be used to calculate the velocity of the vehicle at the start of the skid. So they actually use this in like police crime scenes and things like that to work out if someone was speeding when they crashed. At a test track, a car of mass 1,500 kilograms was collided into the back of a stationary car of 1,200 kilograms. So we have a part A here, but you might notice there's no part B. The part B actually has to do with momentum, which is why I've taken it out, but it will be in the momentum video. The two cars skid along together. So this bit is actually kind of useless for us because it's actually in part B. So skid marks of length 7.5 meters. The car decelerated at 5.6 meters per second squared. Show that the velocity at the start of the skid was 9. Okay. So, what I like to do is I like to write up the letters SUVAT, right? So, S, U, V, A, and T, and I like to label them. So, S in this case is going to be 7.5 meters. U is exactly what we're working out, so I put a big fat question mark. Now, here's where things get a bit interesting. So, do we know the final velocity? Well, it doesn't tell me, except it says to a stop, which means it stops moving, so it's at 0 meters per second. So these are the things you might have to think about. The initial velocity is 0 if it says that it's released from rest or begins accelerating from rest, something like that. The final velocity is 0 if it stops. Okay, that might sound obvious now, but again, can be a bit tricky. Now the car's decelerated at 5.6. So if I imagine what's happening here, we have two cars, which I'm going to draw as a box, travelling this way. They're decelerating, or they're accelerating this way. So I'm going to take this way as positive, okay? So the velocity is going to all be positive, but the acceleration is going to be negative. So it's going to be minus 5.6, and I didn't leave enough room for the time. Do we know the time? No, and we don't actually need it, but I'll still leave a question mark. So the letters we have, and that we want, are S, U, V, and A. So the equation I'm going to be using that has all 4 of those letters. So can't be this one has T. Can't be this one, it has T. Can't be this one, it has T. V squared equals U squared plus 2AS. Okay. Now if you notice V is 0, so I'm just going to make that 0. So if I rearrange for U, I get U is equal to the square root of negative 2AS. Now again, here's where some students might say, oh, there's a negative, panic. But remember, acceleration is negative, okay? So as long as you stay consistent with your signs, I promise you the equations will always work out 100% of the time. So don't worry about it, just make sure that you stick to it. So draw a little diagram, draw which direction is positive, and just stick to it. Any arrows going in the opposite direction to your positive arrow are negative, any going with it are positive. So we have square root negative 2 minus 5.6 times 7.5. Okay. Then all we need to do is use our calculator, which is over here. So we have square root minus 2 minus 5.6. Again, using brackets for everything, just in case some weird stuff happens with the signs. And we get 9.17, which is approximately 9. Which is not too bad, right? 3 marks. Not too tricky in my opinion, but again, it takes practice to get good at it. Now we've got one from AQA. So figure 3 shows a golf ball at rest on a horizontal surface 1.3 meters from a hole. A golfer hits the ball so that it moves horizontally with an initial velocity of 1.8, so that's RU. Deceleration of 1.2 as it travels to the hole. So what we can do here is we can even annotate the diagram they gave us, right? So U is equal to 1.8. I'm going to take this way as positive. My acceleration, which I use a double-headed arrow for, is 1.2. And that's it. So this is calculate the velocity of the ball when it reaches the edge of the hole. We also have the S, which is already given to us, that's why I didn't label it. Okay, so we have S is 1.3. We have U equals 1.8. V is what I'm looking for, right? The final velocity. Acceleration is negative 1.2 because it's going in the wrong direction. And time we don't care and we don't know either. So again, we have S, U, V, and A. And it's the exact same equation as the last question, which is pretty handy. We have V squared equals U squared plus 2AS. So V is just equal to the square root of 1.8 squared plus 2, 1.3 minus 1.2. Yeah, perfect. So we have calculator, right? That's what we need. Square root, we have, again, 1.8 squared plus 2, 1.3, negative 1.2. We get 0.35 meters per second to 2 significant figures. And the reason why I chose 2 significant figures, so another thing that kind of comes up a lot in physics is you have to determine how many significant figures or decimal places you give an answer to. If you look at your question, you find the lowest number of significant figures and you copy that. So in this case we have 2 significant figures, 2 significant figures, so our answer should be to 2 significant figures. If the acceleration was to 3 significant figures, we'd still pick 2, right? If it was to 3 significant figures, of both of them, then we'd pick 3. So it's whatever the lowest number of significant figures is. Here's an OCR question. It's actually a multiple choice. So we have a ball of diameter 2.5 centimeters is held above the ground. The bottom of the ball is 10.2 centimeters above the ground. The ball is released from rest, so initial velocity is 0. Air resistance is negligible, which means the acceleration is a constant 9.81. What is the time taken for the ball to reach the ground? Now, you don't have to draw a diagram for this one, but I'm going to because it just makes sense to. I'm going to draw quite a big ball, and then I'm going to draw the ground down here. Now, from here to the ground, that's a wonderful drawing, 10.2 centimeters. But here's the thing about displacement, right? It goes from the center of mass, right? So it goes from the center of the ball. Okay, so all we need to do is add on the 2.5 centimeters onto that. It goes from the whole width of the ball. So the ball is released from rest. What is the time taken for it to hit the ground? Okay, I'm going to take downwards as positive because there's literally no reason not to. Everything is downwards. And that's going to be our crisp 9.81. So if we half that, so anyways, let's say S equals 12.7 centimeters, which is 0.127 meters. U is 0, V is don't know, A is 9.81, time is don't know. So we're going to be using, so we have SUAT. So if we go to the beginning, SUAT, well, it can't be this one, can't be this one, it can be this one. So S equals UT plus half AT squared. And we're rearranging for time, and again this is going to be 0. Perfect. So I'm going to give you a second just to have a think about this question and if anything is incorrect. So point. And just to have an idea. So, if you notice here, the diameter of the ball is 2.5, but we're looking for the radius, right? We want to get to the middle. Okay, so that's one thing here. So, the reason why I did it that way is because if you sub in 0.127, you actually get a correct answer. You'll get D. Right? Well, I say a correct answer. You get an answer on here. That doesn't necessarily mean you're right, so I was trying to teach you in a lesson here. If you sub in 2.5, you will get the answer D. But that doesn't mean you're right, because again, we're looking for the radius, which is 1.25. Okay? So that's what you need to do instead. So with multiple choice questions, you need to be so extremely careful because they will intentionally screw you over with this, okay? They basically know all of the common mistakes and they work out all of the wrong answers. So instead of 0.127, which will get you the wrong answer, you're going to put in 0.1145, which is just 10.2 plus 1.25 instead. And that is going to be divided by 9.81. And that will give you an answer of 0.152, which is C. And that is the correct answer. So again, just a slight trick to see if you guys were paying attention. Very easy for you to do the right thing, which is to include this number somehow, but do that in a wrong way. Okay? Perfect. So, 2017. So, a motorist receives a speeding penalty notice from the police for a short journey along 120 meters of road. The car specification states that the minimum time for the car to accelerate from 0 to 60 miles per hour is 9.5 seconds. Show that the maximum value for the average acceleration over 9.5 seconds is about 3 meters per second squared. So this is another thing they like to do is unit conversions. They tell us that 1 mile is 1600 meters. So if you think here, 0 to 60 miles per hour. Okay, cool. So with S, we're going to say that that is, we don't know, right? Because we don't actually know how long it's going to be accelerating in terms of distance. U is 0 because it says from 0 to 60. You don't need to convert 0 into meters. Bear in mind that with A-level physics there are some units that when you convert even as 0 size, they convert to something else. So for example, 0 degrees Celsius is not 0 degrees Fahrenheit. Likewise, you also have, what was the other one? There are some others that don't actually translate straight away like that, so just be really, really careful with that. V is, so actually 0 degrees to to Kelvin, right, is also not 1 to 1. Now the 60 miles per hour, we need to convert that. So we take the 60 miles, we times it by 1,600, and we divide it by 60 squared. So why did I get those values? Well, this is miles to meters, right? If 1 mile is 1,600 meters, then 60 miles should be 60 times that, right? So 1 to 1,600, and then we're looking at 60, so we times both sides by 60. Now it says per hour. I want per second. So to convert from hours to second, we times by 60 to get minutes, then times by 60 again to get seconds. Now, why are we dividing it? Well, there's two ways I like to think about it. One is when we have miles per hour, we have miles over hour. So if I'm converting this to seconds, I'm timesing the bottom by 60 squared. So that becomes the bottom of my fraction. And likewise with miles, to times the meters, we're timesing by 1,600, right? So the top gets times. That's one way to think of it. In fact, this is the mathematical way to think of it. The other way to think of it is, let's think, if I'm doing 60 miles in an hour, I should be doing fewer miles in a second, right? Right? It takes me, I'll travel less distance in a smaller amount of time, obviously. So that's also another way to think of it, just to double check. Once you do this, you can be fancy if you want and just do 1,600 over 60, but you know, you don't have to. 60 times 1,600 over 60 squared gives me 26.7 meters per second, I'm going to call it. The acceleration is exactly what I want to, actually the acceleration is what I want to work out, and the time is over 9.5 seconds, so time is 9.5, right? So what are the values we have? We have U, we have V, we want A, and we have T. So this one is going to be the second one here, V equals U plus AT. So again, what I'd advise you do is that when you do these kinds of questions for yourself, write down all of the SUVAT equations on a piece of paper, just have it in front of you, and then as you keep looking, you'll kind of work out what you need to use. So V equals U plus AT. We want A, so I'm going to write A equals V minus U over T. So that's just 26.7, 0 over 9.5. So on my calculator, I'm actually going to keep the exact value. You get 2.81, which of course is approximately 3 meters per second. Cool, not too bad. Part B says the police recorded a maximum speed for the car of 20 meters per second. The motorist knows that the speed at the start and at the end of the 120 meter journey was 0. So we're going to assume that this bit here, by the way, is just designed to confuse, which I kind of hate. Assume it has constant positive acceleration equal to the value in part A for the first 60 meters, and then the same deceleration. So decide whether or not the motorist should challenge the penalty notice. So if you like, you can actually look at this as a velocity time graph, right? Now, the key thing to remember here is for this value here, for the first 60 meters and the last 60 meters, it means that the exact same amount of time has elapsed for the acceleration to take place as well as the deceleration. Both sides of this graph are going to be symmetrical, they're going to be the same, right? Because if you accelerate, if you have constant acceleration, and you accelerate for 10 seconds or 10 meters, and then decelerate for 10 meters, you'll have the same acceleration, you'll have the same distance, and you have the same time either side of that. Okay? So, what we can do is actually half the distance. So what we could do is say that s is equal to 60. Because if we just look at the acceleration bit, the highest value is right after he's accelerated. Okay? That's the highest value for v. We can call it v max if you want. So all we're going to do is work out what that peak velocity was. So when he travelled 60 meters, his initial velocity was 0 because he starts from rest. His final velocity is what we want to know. Acceleration was 2.81. By the way, the reason why they like to say show that questions is so you have error carried forward. So let's say I couldn't do part A. I didn't know how to do it. I can now do part B by assuming 3 meters per second squared, and you will get full marks, right? So my answer was 2.81, right? Let's write that down before I forget. If I work this out with the answer of 2.81, I'll get a certain number. If I work it out with 3, I'll get a different number. But they are both correct with regards to the mark scheme. Okay? So just to reiterate, if you get stuck on part A and you can't do it, and it says part B using the value from part A, just use this value and you will get full marks for part B, assuming you got the right answer for part B. Okay? So no matter what, always try the further parts because you can gain some extra marks. You can gain all of the marks, right? If you get part A wrong, you can do part B, C, D, and E. Okay? Because there's something called error carried forward. Okay? And yeah, we're determining whether or not he actually exceeded 20 meters per second. So the time, we don't know, and I don't particularly care about it. So we have SUVA. I'm wondering if you remember this one already. It's going to be v squared equals u squared plus 2as. Well done if you remembered that. But again, don't worry if you haven't. This will come with practice. Don't know why I drew the square root that big. We have 2.81, 60. And let's do it. Square root. We have 2.81, 60. Let's see if he was speeding 18.4 meters per second. So should he challenge it? Well, he wasn't speeding, he wasn't exceeding 20, so he should challenge it. And almost as if I it's almost as if I scripted the video, explain why the assumptions about the acceleration part B may not be correct. Okay, so this is really interesting because they haven't said why is this answer not necessarily correct. In which case you'll just say the standard, I want you to memorize this, acceleration not constant. That's it. However, they've added a bit more detail. Explain why the assumption isn't true. Okay? So, here it is. 2 marks. Acceleration not constant. And remember, you can always bullet point your answers when it comes to physics. Okay, so there's something like quality of written communication. Bullet points is fine. Quality of written communication only refers to whether or not your answer is in logical order and you've used the words correctly, right? And you haven't contradicted yourself. It doesn't actually refer to bullet points. Bullet point everything, because now I can see, oh look, 1 mark. Second bullet point, oh look, second mark. Easy peasy, right? I can see exactly how many marks I should get. So the question is, why could it not be constant? Well, okay, he's on a road, right? And he's speeding up. Now that means his air resistance is going to increase because he's hitting those air particles harder and harder, right? Acceleration would decrease. So accel would decrease as he speeds up, or as velocity increases if you want to be really technical, because air resistance increases. And again, if you've, maybe you drive, or maybe your parents drive, or whatever, and you've been in a car, when you're on a motorway, for example, going from 0 to 40 is very quick, but then beyond that it gets slower and slower and slower. Why is that? It takes the same amount of energy to accelerate, but the problem is the air resistance is getting bigger and bigger and bigger, which means you have to put into more energy to overcome that. So, that is all we have for today. So we have a good selection of SUVAT questions. Again, if you do have any questions, feel free to put them in the comment section, or you can email them in to me and I can make a video out of it, just going through the whole thing. But that is all we have for these SUVAT questions for today.